Hi everyone, welcome to DNV's presentation on our MedApps activity, which aims to undertake gas leak detection using smart meter data to drive improvements in safety. In our presentation today, we'll give a short overview of our project outcomes. We'll dive into the detailed findings from our phase 1 work, where we've explored how we're using data analytics to detect gas leaks. We'll openly share the insight from our detailed modeling work. We'll dive into the user personas that we've explored, as well as sharing the feedback from our user interviews. We'll then conclude with our proposed business model, our value proposition, and our route to market. Just in terms of who's on the call with me today, so we're DNV. We're here to represent an organisation whose purpose is to safeguard life, property and the environment. My name is Graham Fays. I'm the Growth and Innovation Lead at DNV, and I'm joined here today by my colleagues, Dr. Andrew Phillips, Project Manager, Dr. Chris Bell, Lead Data Analyst, and Joanne Tompkins, Principal Safety Engineer. A very brief introduction to DNV. We're an independent assurance and risk management company, and part of our service offering includes the provision of software, platforms, cyber, and other digital solutions to the energy sector. We have a specific focus on helping our customers manage risk and complexity linked to the energy transition, and specifically the ongoing decarbonisation and digitalisation journeys. Okay, so we want to start with this slide and pose the following questions. Could this incident or these incidents have been prevented? And we started our journey really exploring how gas smart meter data could be used to potentially identify gas leaks in buildings. And sadly, since our work started back in April, we saw another gas explosion take place on the 16th of May in Lancashire. It resulted in loss of life and a number of serious injuries as a result of a gas pipe being cut inside a neighbouring house. Those of you who joined our MedApps kickoff session just a few months ago or have attended one of our own webinars on this topic will know about our project, but to give a really short recap, we aim to analyse the data that is already collected and gathered by gas smart meters and use it for other purposes. We aim to identify potentially dangerous gas leaks in houses by comparing real-time data with previous patterns in gas consumption. We aim to enable efficient planning of maintenance and construction activities, particularly operations that sometimes require portions of the network to be isolated. We aim to detect appliances that are performing inefficiently, driving improvements in terms of energy efficiency for financial and environmental reasons. We aim to detect potential problems upstream in the meter on the gas networks. And finally, we aim to facilitate the conversion of the networks and supplies to hydrogen or hydrogen blends as part of the drive to decarbonise and transition towards net zero. All of these activities, we believe, are activities that could be underpinned through better use of gas smart meter data. So I'm now going to pass to my colleague Chris, who will share some details regarding our approach to this challenge.
Yeah. Hello there, I'm Chris Bell. So I'm going to speak a bit about the modelling side of things that we did for gas leaks and also the analytics that we tried to overlay on top of that to help us detect those gas leaks if they happened. Graham's already mentioned that this study was looking at how we can transition to hydrogen and hydrogen blends. So we have also accounted for that when we did our gas leak modelling to ensure that this solution that we develop now is future-proof and can be used on all types of system as the UK transitions to net zero. For modelling the gas releases, we've modelled 3 different types. We'll call them, for simplicity, small, medium and large. The diameter of these varies from 1 millimetre to 6 millimetres and large, so over 6 millimetres. When we talk about a gas leak here, we're talking about a gas leak downstream of the smart meter. So that's inside the house. And this was modelled a variety of room sizes to determine the time that it would take for the gas composition to reach flammable and explosive concentration levels. The data I'm about to show you is for a detached house with 4 occupants, and we know that it has 1 gas boiler and 1 oven operating in the premises. So this has been used to demonstrate natural gas leak scenarios, which my colleague Andrew will take over later on. Next slide, please, Graham. So from smart meters, they're capturing data and they're sending it to the DCC every half an hour. So this is a typical day for for the gas usage in a household. You can see that at night, the areas marked in red there show no flows of gas. In the morning, we have a peak with people getting up to have a shower, run hot water, cook their breakfast, and that peak also appears in the evening. During the day, we have moderate flows, and these moderate flows are quite interesting. So the data sample we're showing you is from the past year, and obviously this data sample has been taken during COVID times. So this moderate flow that you're seeing is probably anomalous in terms of COVID times, but it's an interesting feature because the algorithms we're developing have to be able to account for this kind of impact on the systems as well. So the solutions we propose here are able to account for people going on holidays, people working different shift patterns and being in the house at different times of day as well. So that has all been accounted for. Next slide, please, Graham. So the first thing we did was we took all the data sources we had available to us for this household. So we had the gas readings, the electric readings. We also knew where the house was located based on postcode. So from that, we could extract the temperature data, which is already given to us through a national grid database. The calorific value of the gas being passed into the house is also measured, is also taken from that source. And there's other things that we can extrapolate from this, such as day of the week, the average over the 24-hour period of gas being used, the month that the gas happened to be used in. All these different days of weeks, etc., correlate with different effects and impacts on gas usage that we see day to day. It's worth saying as well at this point, we also carried out a FMICA, both of the house to understand where gas leaks could occur, but also how this technology could fail in practice, and we've put in adequate mitigation measures to prevent that. Next slide, please, Graham. So the first thing we tried to do, just using a bit of machine learning, was could we identify anomalies in the gas usage data? Now, bear in mind, this gas usage data that I'm speaking about didn't have any gas leaks in it. So it's interesting that we show here, when we look at the probability of something being low, those two red dots you see in the graph there show that for the particular time of day we're looking at, those flow rates of gas through the smart meter are anomalous. So what we're seeing here is we're seeing a false detection of a leak being presented in our data. And if you go to the next slide, Graham, we can complicate the picture even more by putting some of those other features in that I was speaking about earlier, such as calorific value and temperature on the particular day. Those are things that we expect to influence the gas usage in a house. And you can see there that the picture changes quite dramatically again. So the time of day for those false detections has completely changed. And it's actually a bit harder to debug exactly why it's seen that as anomalous. Nevertheless, this is an anomaly detection algorithm, which could be useful, but you have to understand there will be false positive detections, which is something we want to limit as much as possible. If we go to the next slide, please, Graham. So another thing we could try doing was using perhaps more advanced machine learning techniques, similar to the types of techniques you would use when predicting stock prices on the market. So here we've got the blue lines here show the actual gas usage in the house, and the yellow-orange lines show how our algorithms behaved at predicting the usage of gas for that house. So you can see there's a few anomalies detected, quite a lot of anomalies in fact. And in training, the shape of these spikes, peaks and troughs was very good. However, when you actually test it on future predictions and looking into the future, you see the scores a lot less. We've got a score of 6.6 there. The closer your score is to 1, the better. If we go to the next slide. So what we thought was, okay, let's put some confidence intervals on this and see how often that starts to exceed the confidence intervals. Does that help with detection? And yes, it greatly does. If we go back, sorry, Graham, the orange interval that you're seeing there is our prediction with the confidence interval, and the blue spike is what was actually used. So there you can see there's no false detections at all. So this technique does have some relevance. Yep, that's great. Next slide, please. The other interesting thing about gas usage is that during the nighttime period, there was no gas usage at all. So what we did with this data set is we noticed that actually once every 12 hours in a day, the gas usage falls to 0. Now this is important because when we come to look at detecting small leaks, minor leaks in houses, which actually are really, really common, perhaps not flammable, but those small leaks can grow into bigger leaks and of course form explosive mixtures. Then this is a type of anomaly detection algorithm that we can build in to check if there's a minor gas leak, and we can flag that to relevant places. I'll now hand over to Andrew, who's going to speak a bit more about the modelling of the gas leaks and detection of them.
Morning, I'm Andy Phillips. I'm a gas safety engineer, and I did the gas outflow and accumulation calculations. This is a sort of very simplified summary of all the outflow calculations expressing the outflow rate from a leak against the typical gas use for appliances. Now, obviously, it varies a bit from house to house, but typically there's a sort of low-level use band in the yellow at the bottom, sort of mid-level use associated with cooking appliances in the middle, and then the highest use tends to be the boiler, which is the red band. You can see the black curve that runs through them is the predicted gas outflow rate from a leak. And as the diameter increases, you can more or less match the outflow to the gas appliance use in terms of the leak diameters, which is the categories that Chris presented earlier. So you get to anything below about 1 millimeter won't really build up to flammable in most situations and is about equivalent to a hob being left on. Anything up to about 4 millimeters is broadly equivalent, well, sorry, up to about 6, it could be, is broadly equivalent to the maximum gas flow you could ever see through a typical house. In this case, it's less than that. So that blue line at the top is the maximum gas flow that was ever recorded for the property that we looked at. So you can use that as a limit for something that's obviously an unusual gas flow, because if you had all the appliances operating at once, you would never reach that level. So any flow above that would obviously be a leak. On the next slides, we've got some examples of our prototype in use. So in this case, we've modeled some sort of fictional leaks in the real historical gas data. So the black columns in this figure represent the true gas data for that particular day, and the red bits of the columns represent the flow from a fictional leak, if you like. So this is a 4 millimeter diameter leak going in the middle of the night. That falls in our medium category. You can obviously see straight away that the flow is bigger than you've ever seen in that house before, represented by the blue line. So within half an hour of that leak occurring, the algorithm would pick it up and would potentially alarm or report it to the National Centre. And you've got a good chance of preventing that leak becoming flammable and being ignited. You've got several hours typically before that could happen. It might only take half an hour to build up to flammable, but probably there wouldn't be any ignition sources introduced till those people get up in the morning. So you've got ample time to issue a warning and do something about it. So same sort of thing occurring in the middle of the day. Yeah, case 2, please. Yeah, same idea, but it's instantly obvious again on top of the appliance use. So anything around the 4 millimeter size in this case is obvious in the first half an hour. If you reduce it to 3 millimeters on the next slide, it just falls below that critical blue level. So it's a bit harder to detect, but the algorithm would still pick up pretty quickly within the first half an hour that this is unusually high flow rates for that time of day. And it would definitely pick it up at 3:30 in the afternoon, where the combination of the black and the red values goes above that blue line. So the combination of appliances working normally and the leak through the hole is a gas flow that couldn't happen under normal circumstances. So the algorithm would pick it up and would alarm and potentially just cut the gas off. Next case is a very small leak. So this is the type that wouldn't typically build up to flammable, but if it occurs in the middle of the night, that constant non-zero flow between 2 a.m. and 5 a.m. is obviously unusual. There are occasional gas use incidents through the night, just from the normal, so the gas use to the water heater. So that coming on and off might have a spike for half an hour in the middle of the night, but that constant non-zero value would be triggered as an alarm by the algorithm. So it would be obvious within, say, an hour or an hour and a half that there's a gas leak, and that would be alarmed as well. And the last case on the next slide is the same thing happening in the middle of the day. This is probably the hardest case to spot because it's a small leak and the outflow is small relative to the typical, appliance use. So you can't really tell that that's unusual activity. But on the other hand, it's not dangerous either. It would never build up to flammable, but you do pick it up when the appliances are all turned off at about 10 o'clock at night. So although you have to wait 12 hours or so to pick it up, you still detect that release within about a day. So even the small sort of nuisance leaks, we're pretty confident you would pick up. The difficult bit is in the middle between sort of 2 to 5 millimeter range, that sort of moderate size, which could be confused with appliances, and where Chris's algorithms come in to detect anomalies and pick up unusual activity. Okay, so that's all summarized on this slide. So very large leaks you can pick up straight away within the first half-hour reporting period, and quicker if you could access the meter reading more rapidly than that. So at the moment it's only ready every half an hour, but the meter itself does record the flow a lot more frequently than that. So if you could access that data, you could pick it up potentially within a minute or something. Medium-sized leaks are more difficult to detect because they're sort of equivalent to typical appliance use. And the small ones you wouldn't typically pick up in the middle of the day, but you would pick up at night. So even those we're confident you could pick up eventually. So you could pick up almost every release at some point. It's just a question of how quickly you can do it. So on the next slide is a summary of the benefits you'd achieve using this sort of approach. The first thing, as Graham mentioned, was to try and prevent explosions. And depending on exactly how you implement this, you could prevent between about 1/5 and 1.5 lives taken per year. That's on top of any injuries, which are a bit harder to quantify. So there's about 1 life per year would be saved by implementing this. And that equates to about £500,000 to £5 million per year of property damage as well. So just damage to houses and contents. The nuisance leaks are responsible for about 500,000 cubic meters of gas loss. That's unburnt gas just leaking, which is obviously an environmental problem and a financial problem. That doesn't include the small leaks that are detected quite quickly. It's surprising how long it takes people to detect and report a gas leak. And sometimes even when they're detected, it takes people days or weeks to actually report it. So just accounting for those cases, it's 500,000 cubic meters of gas per year. As we went through phase 1, we also thought about using this approach to detect low gas use. So anomalies in terms of not using enough gas rather than there being too much gas being used. And if you look at the national statistics, there are about 32,000 deaths every year from cold winter mortality. So they're not necessarily directly related to purely being cold, but at least a proportion of those cases are. And it wouldn't take much of an improvement to prevent literally hundreds of fuel poverty cases and identifying those and helping those people. In terms of operating the networks, there's more than 400,000 leaks every year reported to the emergency line, which sounds like an awful lot, but that's true pretty much year on year. And even a small improvement in the efficiency of those by determining whether leaks are real or not and what the likely flow rate is going to be and what order to dispatch engineers to investigate those problems would be a big help and would prevent a lot of problems. A lot of people that ring up don't do it deliberately, but give information that isn't actually true in terms of where the leak is or how long they've been smelling it and that sort of thing. So if the system detected those pieces of information and supplied it automatically, it would help prioritize which gas reports to attend first. And on top of that, there's things like legal costs of investigation of accidents, reputational damage that we haven't quantified, but would obviously be helped by this sort of technology. And it would also prevent a lot of small leaks that could lead to larger ones. So we asked several questions at the beginning of phase 1, and we've investigated all of these as part of the work. What proportion of houses could this benefit? And the answer is essentially all of them, so long as you've got a gas smart meter. At the moment, that's about 1/3 of the properties in the UK. We're expecting that to increase. And actually, this sort of technology could be a reason for people to want to install gas smart meters. So over time, we'd expect that to increase, and it could be used on all of those. What size of leaks could be detected? Again, essentially all of them. It's just a matter of time the biggest leaks could be detected really quickly. And those are the ones that tend to cause the most damage, kill people, cause damage to houses, all the rest of it. So the ones that are most likely to ignite and actually cause harm to people are the ones that we're most likely to be able to detect. How many of those explosions could we prevent? Well, it depends exactly how you set it up and how the alarms are reported, whether it's to the householder or the national emergency line or whatever, whether you automatically cut off the gas supply or not. But it's between about 7 and 30% of explosions. But that includes all the very small ones, as I say, small explosions, ones that don't cause a lot of damage. So it's up to about 3/4 of the most severe cases, which tend to be the ones that result in fatalities and large, damage costs.
Okay, so I'm just going to quickly skip through these, conscious of the time, but we just wanted to tell you a little bit more about our user personas that we looked at as part of this project. And we split these into what we might like to do with the data sort of downstream the meter, upstream of the meter, and then overall added value as well. So as we've mentioned, it's all about this dangerous detection of dangerous gas leaks in building. And maybe can we identify if any of the appliances themselves are operating inefficiently? Can we help upstream the meter in terms of the maintenance and construction activities, or if there's any delivery problems upstream the meter in terms of the delivery pressures? And then again, also a number of the project team are working on projects looking at converting the gas network to hydrogen, and we're conscious that there's probably going to be extra mitigation measures that we'll need to introduce as part of that, and this technology would help facilitate that rollout to hydrogen, as well as Andy just mentioned, driving the actual smart meter uptake. It would give individual households an additional reason for actually taking that smart meter, because they've got this extra safety benefit from it as well. So move on to the next slide. So there's numerous different sort of user personas that we've engaged with. We've had meetings with all of these, so including the gas suppliers and the gas networks, housing associations and how this sort of technology might help them managing their properties, insurers and underwriters, whether actually this could be a bit like having, other alarms or security measures fitted. Actually, can it drive down premiums for people that had this fitted? Sort of other academia and enablers and other app developers about how this might fit in with some of the other systems that are being developed. Both HSE and environmental groups, again, looking at how this might be enabled, and regulators and group associations, many of whom we have existing contacts with through our previous work. So it's been really useful to talk to all of those, as well as other sort of data companies as well. So just how we went about our user research as well. So it's really iterative process. We were talking about, who's impacted by this, who are stakeholders, how might this benefit them? Do they see this as value adding to them? And just went through that in a discussion method type process with them, and again kept coming back as a team to review what the information that we'd got from them. We got an awful lot of information from the different people we spoke to, and just processed that, and then went back out with a new set of questions to our next meetings that we had set up. Okay, next slide. Yeah, so some of the typical questions, like we were saying, was can you see the value in this? What sort of technology are you aware of that is already out there? How might this benefit you as a company, as a stakeholder? How might we interact with you on this? So skip to the next one. And then, we just put again some sort of an example of how we've collated the data together and started to, moving into sort of the business model type idea, which I think Graham's going to talk about next, about how we might sort of monetize this and commercialize this in terms of interacting with these different people. Over to you, Graham.
Hi, Graham, you're on mute, but
thanks,
also
Richard.
we're running over on the time quite a bit, so can I ask you to wrap up and we can move on to questions?
Yeah, no problem. I'll maybe go straight to the delivery medium, Richard. Just in terms of delivery models, so we do propose to trial the detection algorithms developed during phase 1 on a large sample of real smart meter data, and aim to develop an API to assess data for gas leaks in real time. So effectively a service that we like to call safety as a service. And for those on the call who are interested in the actual delivery medium, well, we actually think that an API will allow a multitude of different customers and applications to obtain and process our insight and identify issues within households being analysed. And it's absolutely our preferred route to market, and one that's met with considerable excitement from industry, as it allows the benefits that we've outlined to be incorporated into existing tools, apps and solutions that exist today, rather than via another bespoke app that a user, customer or industry has to install. And I think it also allows the amount of data in transit to be reduced and avoids the creation of potential data silos. We've got the basis for the service delivery bill. Openly encourage anybody on the call to head over to the URL shown on the slide and take a look at our platform, which we will use to deliver this final solution. And just an overview of our planned activities for the future. Back to you, Richard.
Great, thank you. And thanks for wrapping up so quickly. So we have a number of questions, and we'll try and get through as many as we can, but we may have to address them in the chat afterwards, just to keep time. So the first one is quite an interesting one, I guess, about the sensitivity of the algorithm. So could you detect a leak in an appliance which only appears when the appliance is in use? For example, an oven with a small leak used when the boiler is not operating, hence would not exceed a maximum household threshold.
Yes, you could. You don't have to exceed that threshold to notice that something odd's going on in the gas use. So particularly if it was at night, which most of these cases are, so someone leaves their oven on, they don't realise the hob isn't lit, that sort of thing. And typically it leaks overnight, builds up, and then someone ignites it in the morning when they get up and start moving around the house. So you could definitely pick up those cases. It would help if you knew exactly what appliances were in the house, but you don't need that to pick up those leaks.
Great, thank you. So what issues have you faced or do you anticipate facing with respect to GDPR and domestic smart meter data access? How do you plan to tackle these issues?
Maybe I can take that. So yeah, GDPR has always been an issue. I guess, first of all, getting access to the smart meter data can be quite time consuming and expensive to do, especially trying to do it on a scale. We have spoken to a few user groups, people who, the enablers, as Joanne called them, who are developing the apps either for energy companies or for third parties to access data. And quite often this relies on people logging into a website and just accepting terms and conditions. So we definitely see that as being, well, it's one of the reasons we've gone down the API route, is because we realise that if people just accept those T's and C's, then that's us, we're past that hurdle quite easily. And it doesn't lock us into a single energy company, if you like. Anybody could build on this solution. So I hope that's answered your question.
Great, thank you. And in terms of your phase 1 work, how many homes did you have data for? Was it just the one you were showing, or was that just an example?
Yep, so there was the one home that we showed, and there was also a data set online which is available. However, the quality of this data set is an old data set from 2010, and the data quality and capture has improved significantly since that study was done. So I'm just going to say one home, but we did have access to the other data sets as well.
Okay, great, thank you. So there's another question about, are the leak cases used of 1 millimeter, the 6 millimeter used in the analysis, the same when considering hydrogen, or will you have more or less sensitivity, or will more or less sensitivity be required to provide the same degree of safety as you've investigated with natural gas?
We ran the gas outflow and accumulation calculations for those 3 gas compositions. So typical natural gas now, a blend of 20% hydrogen and pure hydrogen, and ran through the whole range of leak sizes. And actually you come out with more or less the same answer in terms of the sizes of the holes and how they correspond to appliance use. So the answer is almost the same for hydrogen and natural gas and everything in between. The only difference is for a hydrogen leak, the volumetric outflow is greater, so they tend to build up flammable quicker. So you need to be able to detect the leak and do something about it in a shorter time frame. But the answer is the same and the way the algorithm works is the same.
Okay, great, thank you. Are there any recommended industry standard packages for gas modelling? The person who's asked the question has come across Simulate, AnyLogic, and Simio, but I guess there's other good modelling applications out there.
The modelling we did, it's in a report that we can issue to anyone that's interested. It's based on a fairly simple method that's given in a British standard for the outflow rate. We're not worried about the gas flow in the system in the network upstream of the ECV. It's just purely a leak from a hole inside the building. So it's quite a simple outflow model and then accumulation in a box with perfect mixing. So it's not very complicated, but to demonstrate what we were doing, that was good enough. But if you want to contact me, we can share the details.
Great, thank you. And in terms of how you've been able to integrate with the Open Energy project that's also been going on at the same time, given that you've been looking at metadata, I don't think that's currently in scope for Open Energy, but have there been any other areas you've been able to integrate or benefit from the Open Energy work?
Yep, so we're actually beta testers in the Icebreaker 1 Open Energy Network. So currently going through that just now. You're right, the data at smart meter level isn't available on that network, but we do aim to provide aggregated data sets back. So for example, given the aggregated number of leaks detected for a particular council area, could be of interest to councillors who are looking to plan maintenance, and similar for housing associations. I guess we've also mentioned about the data sets that we use. So there was one from National Grid that we were looking to use for that was done at local area level for getting the temperatures, etc. So yeah, as data like that becomes available, we'll keep an eye out and see if there's anything that we can do there with that.
Okay, brilliant, thank you. And same final question to you. So what are the top 3 data sets on your wish list that you would like to use and possibly having difficulty at obtaining now? And do you know where they're located or who owns them?
Yeah, so yeah, this comes back to, it's kind of similar to the GDPR issue about getting access to data at a mass level. So yeah, so the first thing we'd like to do is to get more smart meter data, just to ensure that the methodologies we're developing now do scale really well. We're confident they do, but we just want to refine things. And especially when you're looking at machine learning algorithms, you want to test that on a much larger scale. And of course, more data makes a more accurate algorithm. So there's a few ways to get this data. As part of phase 2, we're looking to team up with both UCL and the Energy Systems Catapult Living Lab, who have people who are sending them data. And we know the quality of that will be better. So using them. There's also the issue we've had regarding detection times. So currently data from smart meters is sent to DCC every 30 minutes. However, analysing that in the 30-minute period is quite awkward. It's not something that's ever been tested. Most people who extract data from the DCC do it once every 24 hours. But we have been speaking to other innovators who are looking to push this boundary, and there's already a project ongoing which is looking to extract data once every 2 hours. So we're confident that the way the industry is going, that the half-hour reading analyse is going to be feasible. It may just take some time. I guess other data sets we'd like to explore. It was mentioned earlier on about your appliances being inefficient, and also trying to correlate gas usage with particular appliances. So this is something we're looking to do with Living Lab and UCL, whereby a lot of the appliances in the house have been tagged with sort of IoT devices, so you can see exactly when something goes on. Let's say the boiler goes on, and you can calibrate how much gas that boiler is using. Therefore, you can start to pick up this inefficiency in systems as well, and also drive your modelling to be much better at predicting gas leaks.